Um, Good morning for everyone who's here in Australia, and good evening, afternoon for everyone online, and morning. I have the honor today to introduce the Debreu lecture, and it will be given by Professor Chris Shannon, who is a professor of economics and a professor of mathematics at Berkeley. The title of the talk is Random Rationalizability. We will have the opportunity to ask questions at the end of the talk. The questions will be divided between questions online and questions within the room. Thank you, Chris, for, I can't see you. Thank you, Chris, for coming here and presenting the Debreu lecture, and welcome.
Thank you. I'm very happy to be speaking. I wish I were there in person. Let me see if I can share my screen now. Yeah, I'm sure it'll be a fantastic conference, and I know there's been a lot of hard work from the organizers leading up to this, and so I'm very sorry that I can't be there to benefit from all of the work that I know everyone did. But fortunately, we have these ways of being together despite it all. So the project I'm talking about today, this is a paper about randomization in observations in revealed preference problems. And so the paper has sort of two starting points. One is the classic, beautiful Afriot theorem giving conditions on a finite set of observations of prices and consumption bundles that characterize when those could be rationalized as utility maximizing outcomes in a standard consumer problem for some specification for an unobserved, locally non-satiated utility function. So this is a really beautiful foundational result that bridges sort of important basic theory and goes some distance toward addressing sort of real data in the sense that the data here are only partially observable. That is, there's a finite set of observations as a concession to the real world. And two other very important parts of this theorem. One, it's constructive. So when the data can be rationalized, then there's a constructive, simple procedure to give at least some preference relation that rationalizes the data. And second, it's fully non-parametric, so this is not with additional restrictions about a particular class of preferences specified ex ante. So of course, this is a very important result and is a foundation for a lot of important theory, but also for a lot of empirical work that uses revealed preference ideas and tests for basic consumer problems, producer theory, and and related problems. So this is one starting point for the project I'm talking about. A second starting point is important work by Brown and Natskin, which you might think of as maybe starting what has become a huge field of revealed preference tests of all sorts of theories. So the original insight in Brown and Natskin was to think about taking the basic Afriot idea for thinking about rationalizing individual consumer choice into a general equilibrium framework. And so Brown and Natskin showed that there are testable implications for finite data in this environment. Already that was perhaps surprising, coming from maybe some intuitions about the way that general equilibrium problems behave based on things like the Sonnenschein-Mantel-Debreu theorem. And in addition, then they characterized what these testable implications are using some equilibrium version of Afriot inequalities. And so then, more recently, there's been just an explosion of work looking at revealed preference approaches to many different theories. And this is important work both for theory, but also for this interface with data and with empirical applications. This is a place where theory and theorists really have important things to say, so that inform both sides of the question. And so there at the bottom of the slide, there's just a selection of some of the important theories that have some very nice revealed preference work, probably done by a number of people at the conference, and many, many other applications as well. All of this work in some senses, motivated by data, but a lot of this work remains exact. That is, the revealed preference tests that are developed are exact tests. And so this is, in some sense, a very ideal theorist notion of data and what a test should be. And so, if we try to be a little more fair to the data, taking the theory to real data in some sense, then there are things like measurement errors, there are maybe mistakes, things like noisy observations, and so on. And so broadly, the work I'm talking about today, this is trying to think about a general framework for rationalizability and revealed preference problems when there might be errors or there might be noisy observations. And so in the presence of things like errors of some kind in observations, looking for conditions under which some features of the model might be estimated or tested. Okay, so of course, this is definitely not the first paper that is trying to think about errors in revealed preference problems. So even in the original classic work of Afriat, and then the closely related classic work by Varian, you see this theme, other work around that time. And definitely more recently as well, very important papers, and again, just a selection of those here on the slide, are looking at important ways in which theory can inform what we should mean by an error in revealed preference problems. And so in particular, some of what is very nice about some of those papers, particularly some of the more recent papers that are there on that slide, is to really think hard about what should it mean to make an error, or how to measure errors based on particular features of the theory. So in particular, in a consumer demand problem, what does a mistake mean? And so, not just a sort of a brute force, we have the observation plus some epsilon noise term, but in a much more sort of serious theoretical way to think about what we should mean by an error and how to measure that. So what I'm talking about here, this is complementary to this work, but is focusing on a different part of the trade-off. So here, I'm thinking about errors maybe in more general models. And so then there's a trade-off between the sort of scope, the generality of the models that you talk about, and how precise you can be about what you mean by an error. Okay? So in this work, it's going to be maybe a step backwards in that sense relative to some of the lovely recent work that is at the top of the slide, in the sense that the error is going to be more of a black box or more of a crude sort of a notion, but the trade-off will be maybe to try to think about some techniques in more that might be portable for more general environments. And so, of course, this is, again, an enormous literature, and I can't do justice to it in any sort of a short time span, so I'm not trying to here. But let me mention two other very nice recent papers that are particularly related to the things I'm thinking about. So one is a very nice recent paper by Chambers, Echenique, and Lambert, and another is, again, a very nice paper by Christian Ugarte, who's recently finishing Berkeley PhD student. And so these papers are looking at the problem of consistent estimation of preferences. In the case of Chambers, Echenique, and Lambert, this is coming from data on binary choices. And in Ugarte's case, this is coming from, in the classic consumer problem, choices from budget sets. And in each case, these are choices that could allow for mistakes of some kind. And again, part of what's important about this work is being very careful about what is a mistake and thinking about how that is defined, informed by this theory. I mean, but the general questions that they are asking are very much in the spirit of the questions I'm going to talk about today. That is, can you find some conditions for consistent estimation of some aspect of the model in some environment like this? And so for them, the question of estimation is about estimating preferences. And so again, here, what I'm talking about is complementary in the sense that I'm looking for some conditions and some techniques that might allow us to talk about estimation in more general models. So this is not going to be about estimating preferences, but we'll see, they're definitely complementary questions. But again, with the same trade-off then, that making the environment more general then means that you lose the sort of important precision in their papers about what do you mean by a mistake. But we'll come back to that. So the ideas here then will be to, in this sort of coming at the questions from this direction, to think about trying to adapt some techniques from SAET estimation and from an enormous literature in what's should be called topological data analysis. So these again are both enormous literatures I couldn't do justice to here, but as we go along, I'll try to highlight the particular things that are being adapted here for the questions that I'm going to talk about. And so a broad overview, the results will have the flavor of being able to give a consistent estimator of the model under some conditions, and secondly, under some weaker conditions, maybe to give a consistent estimator for some features of the model that are based on the topology of the model. Okay, and so just as a sort of a tag line about what that might mean. So this is going to mean that you're not, in some sense, estimating the model, but you're estimating the homology of the model. So I'm going to leave that as an enormous black box, definitely for the talk, and even really for the paper. In some sense, a nice aspect of the results is that the results could be understood, and in particular, the applications I have in mind, with just a very minimal understanding of what is in that box of homology. But this is a theme, a big theme in the work on topological data analysis, that you might be able to recover some aspects that are purely topological about something you're trying to estimate that then might inform you about some of the important features of the model. And so for our purposes here, those features will be things that can be understood more simply, like the number of equilibria and things like that. Okay, so most likely for the talk, I won't have time to talk about those results in any case. But even if I do get to talk about those results a little bit, like I said, I'm going to leave exactly, sort of what that means as more of a black box. Okay, but again, maybe we will be able to talk about that a little bit later. And so just before we get into the results, just a couple of, sort of warnings. The first is there won't be anything magical here, in the sense that there will be some strong assumptions on the models, and there will be some strong assumptions on particularly the distribution of noise in order to make some progress. But in general, these are questions, broadly, that are sort of important questions, both for theory and for the interface with empirical applications. And that's a point that's been emphasized a lot in sort of all of the revealed preference work going way back. And so it's useful to have maybe as many different kinds of tools as possible to think about these questions. And so the last sort of warning I'll have is this is definitely a theoretical paper. It's a paper about theoretical data. So both in the sense of making strong assumptions, but also any data related to this will be purely theoretical. So no data was harmed in the making of this paper. So I definitely will not. I will not have a data set that is in any way real in this paper or in this talk. Okay, so with that as a background, let me set up some preliminaries first. So, in the background, the idea is we're thinking about some observable variables. They live in Rn. So the set X here, this is whatever it is that describes what is observable about the problem. D is just going to be the standard metric on Rn. So the idea of what is given by the theory, whatever it is some restriction on what might observable subsets might arise. So this is given by this collection calligraphic M. So this is a collection of subsets of X. Okay, so the idea here is an element in this collection is some particular subset of X, which corresponds to some particular restrictions that a version of the theory might impose. Okay, so this might be the set of restrictions that are consistent with utility maximization over the budget set for Afriot's problem. And then a particular element in this collection would be, well, what restrictions are generated by specifying a particular preference relation or a particular utility function. Okay, so we'll do that example in a second, but that's something to have in your mind. So then the idea is the analyst observes some data set, some set of observations. And so that is, again, just some subset of whatever the observable variables might be. Okay, so for now, details about that set will be general. This could be a finite set. It could be an infinite set. We're going to be thinking here about finite data sets that are in particular generated by some random variables. Okay, but for now, this could be something general. And so you could just think about a very simple exact notion of rationalizability in this framework as saying that your data set is rationalizable if there's some particular model in your collection that contains your data set. Okay. Okay, so the two examples that I'm going to use today to motivate this, first, the classic consumer demand problem. Okay, so this, think about the demand problem with L goods. So here, think about the observable variables then being price vectors, income, and consumption bundles. Okay, so a particular data set then would be some collection of such observations. So tuples of price vectors, income, and consumption bundles. And then what are the models then in this setup? Okay, so the models then, these are just sets that correspond to graphs of demand correspondences that would be generated by some locally non-satiated preferences or some locally non-satiated utility function, the way that I've written it here. Okay, so that's what the big expression there that's displayed says. So a model in this case, it is exactly what that says. It's the graph of the demand correspondence for some locally non-satiated utility function. Okay, so that's a way to think about the classic setting for Afriot's theorem. Here, in that case, the observations, the data set is finite, or all sorts of other classic problems in demand theory, for example, integrability or things like that. Okay. So the second example that I'm going to use to motivate things is the exchange equilibrium example. So here, for notational reasons, I want to think of this as an exchange economy with L+1 goods and M agents. And so here, what is observable? So here, the idea is what the analyst can observe are price vectors and a profile of initial endowments for the consumers. Okay, so here, for this example, I'm going to normalize the price for the L plus first good to be 1. So this is looking ahead, trying to ease the notational burden down the road. And so here then, a data set would be some particular collection of price vectors and profiles of initial endowments for the M consumers then. So what's a model then in this environment? Okay, so again, a model is going to look complicated but be very natural. So it is just the graph of the equilibrium correspondence for some specification for locally non-satiated utilities for each of the M agents in the model, in the economy. And so again, this is unpacking what this displayed equation here says. Okay, so this says a model is all the possible prices and endowment profiles for which 0 is an element of the aggregate excess demand correspondence at that price vector P, and for that initial endowment profile omega. And the notation here, the Z with the E, the subscript, so that's the aggregate excess demand correspondence that's generated in this economy. And so the E notation is keeping track of the utilities of the M agents. Okay, so that's the notation. Okay, so this is the way we could think about the setting for the general equilibrium model with unobservable consumption. So that's as in Brown and Matzkin. So there, the data set would be finite. Or, for example, in this very nice paper by Chiappori, Eklund, Kubler, and Polemarchakis, where this is an infinite data set. This is maybe a version of integrability for this problem. So before we go on, just a notational warning here. Again, looking ahead, trying to ease the notational burden for myself going forward. Here, this Z, the excess demand here, this is already incorporating Walras law. So this is excess demand for only goods 1 through L. Okay, so those of you maybe taking the title of this session seriously, and coming to think about general equilibrium, might anticipate why that will help with the notation. But in any case, just a minor notational warning there. And then omega here, this is just standing for the profile of initial endowments. Okay, so those are maybe two then examples to have kind of in the background, thinking then about the kind of questions that I want to ask a little more generally. Okay, so stepping back then to a more general frame, setting. So the underlying framework here then will be to think about this general kind of problem in which the data is generated by some random variables. So these will be, say, n random variables. For now, imagine that these are, say, independent random variables. And so then a particular data set here you would think of as then the realization of those n random variables, a particular realization of those n random variables. So in the background, the idea is then what we actually observe, these are noisy samples in some sense from an unknown model, from an unknown set, maybe in Rn. Okay, so from one of the models maybe that our theory might generate. So then the two broad questions that the results I'm going to talk about today are trying to address. So first, could this model be estimated in some sense from the data, say for n sufficiently large? And could features of these models that have generated the set be estimated in some sense, again, using the data, maybe for n sufficiently large? And then, of course, in the background here already might be, what does that even mean? Okay, so again, it's not obvious what that should mean at this level of generality. So part of the task will be to try to make sense of the question. So again, let me start with maybe trying to give a broad sense of what the answers will be. Okay, so where we're going to go will be to try to show that for, say, a certain class of sets, then we can give positive answers to both of those questions. So the model could be estimated from the data if the noise is sufficiently small. in a way that I'll make precise. And also that under some weaker conditions on the noise, then we might be able to estimate some features of the model. Okay, and so as I said, in particular in this black box, the homology. And then from that estimation, we might be able to infer some features of the model. For example, the number of equilibria in the model. And then important test here of whether this is useful for us. So examples then of problems that will fit into this class, then smooth demand and smooth economies in the sense of Debreu's classic work. So the paper has other examples, in particular finite games with strategic complementarities, but I'm not going to talk about that here today. And again, the examples are in part to try to illustrate what might be sort of useful about trying to take this other sort of more general perspective that definitely loses some of the important precision in being able to talk about what you mean about what should an error be and what's a reasonable assumption to make about errors that is tied more closely to a more specific model. Okay, so the first idea I want to try to sketch is then what is this class of sets, and so this is the idea of the reach of a set, which is a notion of curvature coming from some classic work of Federer. And so I'll try to sketch the definition first, try to illustrate what it means, and then we'll talk about why this is a useful concept for these kinds of questions and sort of how it is tied into the answers. So first, just to try to define the concept. So think about a particular set A in Rn. And so I'm going to try to define this notion, the reach of the set. And so the definition will go in two steps. Okay, so first, I'm going to define the reach of the set at a particular point. Okay, so for that, fix a point little a in the set A, and define the reach of the set A at the point little a to be the supremum of all the real numbers C with the feature that any point X in a ball of radius C around the point A has a unique nearest point in the set A. Okay, so this is notation here. This is the open ball of radius C around the point A. Okay, so with this as the definition of the reach of the set at a particular point, okay, then the reach of the set overall, this is defined to be the inf over all points little a in the set of the reach of the set at that point little a. Okay, so let me try to illustrate this in a couple of pictures, and then this is going to be a central idea for all of the results that I'm going to tell you about. And so I'm going to try to emphasize what this means and why it's useful in a couple of different ways. But let me start maybe just with a couple of pictures to try to illustrate what the notion is. Okay, so first of all, we could just think about here's a candidate A for the set in question. This is the squiggly blue line on my picture. So we can think about what is being asked here, say at the particular point little a in the picture. Okay, so for example, if I look at the point little a and I think about this point X here, so however far this point X is from A, then whatever I'm doing here, I've gone too far in the sense that this point X here does not have a unique nearest point in the set capital A. It has, for example, 2, maybe at least, maybe more. My picture maybe not particularly precise, but in any case, this point X here we've gone too far. So this is a distance larger than we're asking for. Okay, so let's maybe change a little bit. Okay, so instead, so again, looking at the point little a here, if I come a little bit closer to the point little a, then perhaps to the point y, now it looks more like I might be close enough to a such that any point a distance less than this to the point little a would have a unique closest point in the set capital A. Okay, so I realize in my picture here, I probably should have made a little ball around the point little a there. But the illustration being that this might not be true for an arbitrary choice of a ball around the point little a, okay, but if I'm careful and make the ball small enough, then I could find some sufficiently small ball around the point little a such that every point in that ball would have a unique nearest point in the set capital A. Okay, so this is illustrating the idea that the reach of my set capital A at this point little a is some positive number. Okay, and then perhaps if that was plausible, then that I could do the same construction at every point in my set capital A. Okay, so maybe that number would change, but that if I look then maybe at the inf over all the points little a in my set, then that remains a positive number. Okay, so the idea being that there is some distance sufficiently small that I can perturb away from my set A and still be sure that everywhere in that neighborhood around A, then all those points have a uniquely identified nearest point in A. Okay, so this is trying to illustrate the notion of what it would mean if the set had positive reach. Okay, so how about an example that doesn't behave like that? Okay, so think instead about this set A here. So that has this, for example, kink there at that point little a. So if I think about the same construction here, then from that point little a, I notice that in some direction, so in particular in the direction that's indicated there in the figure, then no matter how close I am to that point little a, then as I move along in that direction, no point there on that ray has a unique nearest point in capital A. So regardless of how close I am to that point little a. Okay, so this is a case where the reach of the set at that point little a is 0, and then overall the reach of the set A would be 0. Okay, so the idea of this notion is that it is somehow encoding something about how stable the features of the set A are with respect to sufficiently small perturbations. Okay, and in particular that the sets that have positive reach, so ones like this picture is trying to illustrate, then they in some sense might be well behaved under sufficiently small perturbations. That sufficiently small perturbations are enough like the original set that this might be useful. Okay, so that's the theme of the basic results I'm going to talk about. And this is a theme much more broadly in a variety of different results in set estimation and in sort of topological data analysis more broadly. So a condition and related conditions that were identified in various different ways and sometimes under different names. Okay, but one of the nice things about some of the results I'm going to talk about today is that they all can be derived just from this basic property, the property of whether the reach is positive or not. Okay, and so broadly, the idea is that sets for which the reach is positive maybe have various nice features, and in particular that they may share some nice features of both smooth manifolds and of convex sets. Yeah, so those are very different in general. But in this sense, they have some similar nice properties. In particular, a compact manifold always has a positive reach. That is not too hard to see in the end. And then the second, that the reach of the set is infinite if and only if the set is closed and convex. And so a theme of the results I'm going to talk about is that the larger is the reach, the better is something that you'd like, the easier it is to do something that you might like to do. And so eventually then the fact that this becomes easiest in this case when the sets are closed and convex then might make sense as a sort of a dropping out as a side point. But in particular then, what I'll try to illustrate that this is a condition that is satisfied under some natural additional restrictions in the examples that we talked about, and also that this might look like a very complicated property somehow to be checking for, but in fact it's actually not that difficult, and in particular that some nice results in Federer characterize some simple conditions under which this the reach would be positive. In particular, looking at sort of canonical examples like sets that are defined by families of equalities and inequalities, then the reach would be positive under some additional smoothness conditions on those equations and inequalities, and under some natural conditions about independence of the gradients of the functions that are involved. And so that sort of a characterization in particular will make it straightforward in the examples that I talked about to find some natural sufficient conditions, additional restrictions under which this positive reach condition would be satisfied. Okay, so let me maybe go to those to try to illustrate. Okay, so for example, in the demand case, then I'm going to add two additional conditions. So the first is that these are generated by smooth demand functions that I'll define in a second. And the second, that the prices and incomes that are observed, these are drawn from some fixed interval, for example. Okay, so this means I'm looking at a restricted class of models that are now graphs of demand functions for the restricted price and income pairs in this interval, and where in addition, I'm going to think that the demand function is a C1 function that has a locally Lipschitz derivative. Okay, so I'm going to make the assumptions just directly on the demand function here. If we wanted to, we could, of course, go back and talk about conditions on primitives, on preferences and utilities that would generate demands with those properties, but that is not the the most important thing here. Okay, so in addition, then this interval, imagine that the endpoints P1 and P2, these are strictly positive. P1 is strictly greater than P2. Similarly, the incomes both positive. Y2 is greater than Y1. Okay, so those restrictions will imply that the models then for those restriction conditions are all compact. So these are all compact sets. And in addition, that the reach of each such set is positive. So this is not completely obvious. Like I said, the general notion of reach is a little opaque maybe, but like I said, it's not too difficult to check this. Basically, looking at conditions on, what are some sufficient conditions for families of equalities and inequalities coming from, particular this result of Federer's that I mentioned. So, right. So for the demand example, those are some additional conditions under which all of the possible models would correspond to compact sets that have positive reach. Okay, so we could do a similar exercise for the exchange case. So here again, I'm going to add some conditions. So first, that the economies are smooth economies that I will define in a second. And then second, that again, the endowments are drawn from some interval. So I'll say more about that in a second as well. Okay, so for the smooth economy restriction, so here again, I'm not going to try to make the most primitive conditions for the properties that I want here. So here the restrictions will be, for example, preferences are strongly monotone, individual demands are unique. So we have an aggregate excess demand function rather than a correspondence. In addition, the aggregate excess demand function is C1 and has a locally Lipschitz derivative. And so again, we have well understood conditions on utilities, for example, that would generate the demand and excess demand that have those properties. Okay, so then in this case, the models, again, these are now graphs of excess demand functions, then, graphs of the equilibrium correspondence now generated by this well-behaved excess demand, aggregate excess demand function when the endowments are restricted to this particular interval. Okay, so for this example, then I want one more restriction in order to see that all of these models now will have a positive reach. And so that'll be a restriction on this interval that constrains the endowments. Okay, so here, given a smooth economy, I'll say that the interval omega 1, omega 2 is a regular interval for the economy if first these are two strictly positive endowment profiles, and the upper endpoint omega 2 is strictly greater than the lower endpoint. And in addition, for any endowment profile on the boundary of this interval, the economy with that fixed endowment profile is a regular economy. So this is in the sense of Debreu's classic work. Okay, so here's a reminder what that means. So this is saying that for this fixed endowment profile, the derivative of the excess aggregate excess demand with respect to prices has full rank for any equilibrium price vector in the economy that has this fixed endowment profile. Okay, so with that additional restriction, then on the interval that constrains the endowments, if the economy is a smooth economy and the interval of endowments is a regular interval for the economy, then the corresponding set, the set of prices and endowment profiles that are for which the aggregate excess demand in the economy is zero. Okay, so this piece of the equilibrium correspondence in this economy, that is a compact set and it has a positive reach. Okay, and again, this would be, like I said, not obvious, but coming from this general result about conditions for families of equalities and inequalities to generate a set that has a positive reach. Okay, so with two examples, so our sort of two motivating examples in which we can see some natural conditions under which the models that would be generated would satisfy these properties. So that's going to motivate us to so to go ahead and to take then as a general condition to think that the models that we are studying then are compact sets that have positive reach. Okay, so that's going to motivate optimism that may be a sufficiently general condition that it could be something that could generate some sort of general results that we could apply in a variety of different settings. Okay, so so now we're going to imagine that the sets in question are compact sets that have positive reach. So I'm going to try to sketch the idea then for a result about some conditions under which it might be possible to estimate a set like this. Okay, so a little bit of notation first. Think about the sort of epsilon neighborhood around this set. So for some positive epsilon, all the points that are a distance less than epsilon from this set. So roughly the idea for the estimation technique I'm going to talk about is the idea that if we could perhaps estimate both, say, the closed epsilon neighborhood around the set M, and also estimate, say, the boundary of that closed epsilon neighborhood around M, using our data, using the random variables that generate the data, then maybe it would be possible to estimate the set that generated that neighborhood by looking at the estimated points of this neighborhood that are a maximum distance from the estimated boundary of that set. Okay, so broadly, this is an idea in a variety of different constructions in sort of set estimation. So this puts together a sort of a standard sort of naive way of estimating a set, the Debreu-Wise estimator, and some techniques, in particular from work by Cuevas and Rodriguez-Casal, about this problem of being able to estimate simultaneously both a set and its boundary. Okay, so I'm going to try to sketch that idea, which is going to be the idea behind the construction for the result. And along the way, try to then illustrate the additional assumptions that will be needed in order for this estimator to be well behaved. Okay, so the basic setup, we're thinking we have random variables that are generating the data. So now let's be more specific about how those are behaved. So imagine that these random variables are IID. They're distributed according to some probability measure mu. And now let's imagine that mu has a support, which is this closed epsilon neighborhood around M. And so this is the idea that the noise is small. It's concentrated on this epsilon neighborhood around the set. Okay, so the first step in the procedure, so think about some sequence epsilon n. The epsilon n's are all positive, and think about a particular draw from these random variables. So this is generating the particular data set that we see here, x1 up to xn. Okay, so sort of a simple, naive way we could use this data to try to estimate the set, the support of the random variables would be look at the set here that's called S hat epsilon n, which is just the union of closed balls of radius epsilon n around the data points xi. Okay, so this is the naive sort of Debreu-Wise estimator of the set. Okay, so here's back in my picture trying to illustrate this. Okay, so now if the squiggly figure is the set M that I'm trying to estimate, then if the scattered points there, if those are the points that I observe, then given my epsilon n, whatever that is, then my estimate of now my set, it looks like the union of those closed balls. Okay, so this is maybe maybe the first thing we might think to try. Okay, so now the goal was to try to find an estimator for the set M here. Okay, and so like I said, maybe an idea might be to try to estimate this neighborhood around the set M, and then also to try to estimate the boundary of this neighborhood, and then to try to recover the set M by looking at all of the points then in my estimate of this neighborhood that are a maximum distance from the boundary. Okay, so going back maybe to this picture might maybe help a little bit to see why something like that might be related to the set M that we started with. Okay, so if we knew the neighborhood around the set and we knew its boundary, then maybe we could recover M. Okay, so this is the idea for how we will try to estimate M. Okay, and so to set that up, so from then the set, the S hat epsilon n, from our estimate of this closed epsilon neighborhood around our set M, then let's look at this estimate R hat n, which is the maximum distance points in the set S hat epsilon n can have from the boundary of that set. And then pick out in our estimator M hat epsilon n all the points in our estimated set that are a distance from the boundary, from the estimated boundary, at least this r hat n minus 2 epsilon n. Okay. Why should that be at all related to m? Okay, so there's a result. So there's a reason to have made this, gone through this construction. Okay, so let's try to see what that result might be. So first, what would we even mean by a good estimate of the set? So here, I'm going to ask that the Hausdorff distance between the estimator and the set goes to 0, then again, in some sense. Okay, so that'll be maybe a strong request about the notion of convergence, that this be something that converges with respect to the Hausdorff distance. Okay, so here's a reminder on this slide about what the Hausdorff distance in general between two sets would be. Okay, and so the idea of the construction here is that under the conditions, in particular the set M, is a compact set that has positive reach, and under some additional conditions on the noise, in fact, this construction will generate an estimator that converges in Hausdorff distance in an appropriate sense. And so in particular, we'll see we will get this to be strongly consistent. That is, the convergence will be almost sure. So let me try to sketch how that goes. Okay. So for this, so we are thinking about the set M. It's a compact set. It has positive reach. I'm going to add an additional requirement that the set have an empty interior. So you can think of this as, say, a lower dimensional set in Rn. And checking quickly the examples we talked about, it's not hard to see that that additional condition is satisfied for the demand example and for the equilibrium example. So in another slide, I'll get to why that additional condition is useful here. Okay. I'm going to add a few more assumptions now to the noise. Okay, so we started with the assumption that the noise has a support, which is this closed epsilon neighborhood around M. So it's small with respect to the set M. In addition, now I'm going to assume that this epsilon is something less than the reach of the set M. And then in addition, that the distribution mu has a positive density with respect to the Lebesgue measure that is bounded bounded away from 0. Okay, so why is that useful? That's useful because the property that the reach being positive tells us about the set M is that it is sufficiently stable in some sense with respect to sufficiently small perturbations. So what that will mean is that the set and this epsilon neighborhood around the set, in some sense, behave very similarly when epsilon is small enough, in particular when epsilon is smaller than the reach of the set. And in addition, the set M, this epsilon neighborhood around the set M, and also the boundary of this epsilon neighborhood around the set M, all behave in some sense very similarly when the set has positive reach and when we are moving just within some epsilon neighborhood that is within the reach of the set. Okay, so all of those ideas are in the background, then will let us make use of some very nice results from Cuevas and Rodriguez-Casal, which give conditions in general for the simultaneous estimation of the set and its boundary in the sense of the Hausdorff distance that we were talking about. Okay, so their question in general is to give conditions under which, with probability 1, so almost surely, for n sufficiently large, the Hausdorff distance from the estimated set and between the estimated set and the set is less than or equal to the constant epsilon n. And in addition, the Hausdorff distance between the boundary of the estimated set and the boundary of the actual set is also less than or equal to the same epsilon n for an appropriate choice of these constants epsilon n. So here, the appropriate choice is some constant scalar of a power of log n over n. Okay, so what is that constant? So that is a constant that is chosen so that you're sure that you're sort of covering enough of both the set and its boundary in order to be able to carry out this simultaneous estimation at the same rate with respect to the Hausdorff distance. And so exactly what that is, probably on a slide or two, we might be able to see. But what's important about this result is that this gives conditions under which the set and its boundary can be simultaneously estimated with respect to the Hausdorff distance at the same rate. And in addition, telling what that rate is. So roughly big O of log n over n. And so this can be done under some regularity conditions on the set, and in particular that have a similar flavor to the conditions that we've been talking about. Okay, so these are slightly different, but in particular, that would be satisfied if the set that we're trying to estimate looks like a closed epsilon neighborhood around our set M, which is a compact set with positive reach. And so roughly this is the same sort of property. So the question here of trying to simultaneously estimate the set and its boundary is something that is possible when the boundary of the set is sufficiently regular and behaves in a way that is sufficiently like the entire set. Okay, so in particular, this is loosely what it is that it buys you when what you're trying to do is estimate, say, an epsilon neighborhood around a set that has positive reach. So that guarantees you that the set you're trying to estimate M, that its epsilon neighborhood, and that the boundary of this epsilon neighborhood in some sense are all similarly behaved. Okay, so in any case, that results in the background then doing the hard work. And so the other two pieces then, the fact that the set has positive reach and that it has an empty interior. So this guarantees that the set is exactly all of the points in this epsilon neighborhood around the set, which are the distance epsilon from the boundary, and that these are exactly the points that are the maximum distance from the boundary in the real set. Okay, and so this is why the estimation procedure that I sketched then would be successful then in this case. So putting together those observations with the results from Cuevas and Rodriguez-Casal, then with probability 1 for all n sufficiently large, then the Hausdorff distance between the estimator of M and M is less than or equal to maybe 4 epsilon n. And here again, epsilon n, this is the order of log n over n. Okay, so that's a sketch of the results about estimation, that is conditions under which then it would be possible to give then a consistent estimator of the set. And so, so as I sketched, this is strong consistency in the sense of almost sure convergence, and in the sense of the estimate being with respect to the Hausdorff distance. So I'm coming to the end of time, so let me maybe just in a few, so that those slides were collecting together the assumptions about the distribution of the noise, and then a statement of the theorem that we just sketched. So let me maybe try to illustrate then, and I'll end on this illustration with then what this might say for the example of the exchange equilibrium. Okay, so here, for this example, a little bit of notation first. So we have the true model, M, generated by the true economy in the background there. So think about for each endowment profile, omega, the corresponding set of true equilibrium prices in that model. So that's the set M of omega. And then think about what we have estimated here. Okay, so we've generated our estimate M hat of the true model. And so correspondingly for each endowment profile omega, we could look at the estimated set of equilibrium prices. Okay, so this is whatever it is, the P's such that the pair P omega are contained in our estimate M hat. Okay, so then the result would be if the underlying model is a smooth economy and the interval of endowment profiles is a regular interval for that economy, okay? And in addition, if our data are generated by random variables satisfying the assumptions that we just laid out, okay? So then with probability 1 for n sufficiently large, we'd have two things. First, the set of real equilibrium prices, this would be contained in our estimate of the equilibrium prices for each endowment profile. And second, that the Hausdorff distance between those two sets, between the estimated set of prices and the real set of prices, this would be bounded by 4 epsilon n here, where our epsilon n term, this is big O log n over n. Okay, and this is uniformly then for all of the endowment profiles in this interval. Okay, so so I'm out of time, so that's in any case a good place to end. So like I anticipated, I don't have time to talk about the second set of results that are about weaker conditions on the noise, but that was, I guess, as I anticipated. So let me skip those slides and just say thank you.
Thank you. Hello. We'll open the floor to questions, and then we'll go to online questions. George.
Hi, Chris. Very interesting. So your notion of a model is all deterministic. Does this analysis allow you to think about models that have a stochastic component?
What do you have in mind?
Many of the models that we many of the models that we study involve some sort of randomization or some sort of intrinsic noise rather than just errors that are being made. And as far as I could understand from your analysis, everything is built on deterministic assumptions.
Yeah, so this would be so, you know, this is the danger of having something that's so you know, so general that, you know, my first reaction to your question was, you know, probably anything would fit at some level. I think the closest thing to think about is what's deterministic is the set M. And then what is a big black box is what is, I'm looking for a slide where this might be, maybe here. You know, what are actually these random variables? So there it might be that what is generating randomness in the observations is not just, you know, we don't observe the prices exactly, but is something more along the lines of what you have in mind, which is some kind of randomization in the actual model. So maybe it's in the consumer problem, people don't optimize exactly, they may make errors of some kind, or maybe in a game, you get a noisy signal of what your opponent does. And so that's where noise might be generated away from what would have been maybe a deterministic ideal, which would have been, what would the equilibrium be if you exactly, if you knew your opponent's type or something like that. So while it's an enormous black box, that would, I think, be where you would try to insert some kinds of stochastic elements.
Thanks.
Any other questions from the floor? I've got a question, Chris. So with regards to the errors, just looking at the exchange economy example, can we understand the errors as being errors about the primary preferences and endowments? So basically, can we understand it as you don't know what the preferences and the endowments are random, okay? They're very close to the preferences and endowments of the deterministic economy. Given a realization of the preferences and endowments that are random, you get your own M, which is their own M, which is the equilibrium manifold. And so you've got the whole manifold moving around, and you're observing points on this moving around randomized equilibrium manifold. And can we understand it as you're observing some sort of structural problem with the economy, whereby you've got prices and there's excess demand or excess supply. You're not always at equilibrium, okay? Mm-hmm. And you're not actually observing, I mean, the manifold essentially says you're always going to be at equilibrium. You've got these random things happening, but you're always going to be at equilibrium. Which interpretation are we thinking about in this black box about the errors?
So in general, it could probably be either. And let me try to find, let's go this way. Let's take this picture, for example. So maybe the squiggly blue line there, that's my equilibrium manifold in the true, maybe there's a true model. So why are the observations noisy? So it could be, I think, you could probably write either version that there's some stochastic element in the preferences and or endowments that so that what you're observing are maybe actual equilibrium prices in nearby economies, or it could be that you're observing approximate equilibria in some sense. So equilibria where with respect to either the true preferences or maybe some other preferences that where you have violations of market clearing for some of the goods. So with where you would have to then work hard would be starting from with primitive conditions, whichever ones version you wanted, whether it's there's a stochastic element to utilities and endowments, or whether it's there's some kind of approximate equilibrium generating the data. Then you would want additional more primitive conditions such that the implied distribution then would have the properties that that the theorem requires. that makes sense. So, so the theorem says, under these conditions on the distribution mu, something nice happens. But then, it would be, if you want to be more specific about what generated mu, could you tie more specific conditions to these general properties? Does that?
Yeah. So I'm thinking about the random manifold case, that if you're at equilibrium, it's just the economy, you don't know which economy is actually realizing. And in that case, your conditions would likely require some sort of lower homocontinuity of the manifolds. So as the economy gets closer, the manifold converges to the manifold, right? Rather than the approximate equilibrium. The approximate equilibrium, yeah, that I buy that. It's just how the manifold moves as you perturb the underlying data of the economy and stay at equilibrium.
Yeah, so again, I think so two possibilities. One is you might want to ask that question, separately, sort of not try to fit it into this result. But if one wanted to try to fit that into this result, the issue would be whether the randomness you have in mind would generate a distribution mu that that has the properties that it needs to have for the theorem. So I don't know if that would be possible or not, but that would be the question to ask. And also, it might be that partly you are thinking about a slightly different and important question. So again, here the exercise was M is fixed. The M you're thinking you might be able to estimate is fixed. So if it's it's the equilibrium manifold generated by some family of preferences, and what's generating the randomness in the data is maybe people are actually have randomness in their preferences. Still, the exercise is I'm trying to estimate the equilibrium manifolds for some fixed set of preferences.
Mm-hmm. Okay. Thank you. Are there any questions from the floor, from the live floor? There are no questions from the virtual floor. Thank you very much, and thank you for, it must be middle of the night with you. Thank you for, we're honored to have you as a guest, virtual guest at the Australian National University and in SAET. So thank you, everyone.
Thanks, everyone.